So the title of our presentation is Parametric Joint Confidence Level Analysis, which is a practical cost and schedule risk management approach. So to start with our agenda, for our introduction, we're going to talk about what is JCL analysis, Joint Confidence Level Analysis, and machine learning. What are the motivations and what are the benefits of each of those analyses? Next, we'll talk about two different JCL methods. One is the commonly known bottoms-up method, and then we're going to introduce another method for JCL analysis using the top-down parametric approach. And then we're going to talk about machine learning and how the different machine learning methods can play into top-down JCL approach for parametric use, which include optimization or regression trees. Next, we'll talk about how do you incorporate uncertainty analysis in parametric approach when you're conducting a top-down parametric JCL. And then we'll introduce a Microsoft Excel JCL calculator that you can use to implement the top-down parametric method. Then we'll show some JCL results, what are example outputs that you could show to management, and then we'll introduce a case study from NASA agency that used the top-down parametric approach for JCL analysis. So what is joint confidence level analysis and how would machine learning techniques play into that analysis? The JCL is a more holistic view of uncertainty. It integrates the uncertainty of cost and schedule and is a process of combining the project's cost, schedule, and risk analysis into a complete picture. The joint probability approach calculation would combine the individual costs and schedule risk analyses into a joint probability distribution. The goal is to identify the probability that a given cost and schedule would be equal to or less than the targeted cost and schedule. Because it's a more stringent requirement, the joint confidence level is almost always higher than the cost or schedule confidence when modeled separately. Machine learning, on the other hand, represents a variety of statistical methods for prediction and classification. Some traditional machine learning methods include regression analysis, clustering, and optimization. Some newer machine learning methods include decision trees, deep learning, text analytics, and reinforcement learning. The newer machine learning methods are computationally intense and they require programming tools to run many iterations of algorithms in a short period of time. Now I'll hand it over to Christian to discuss the motivation behind a joint confidence level analysis.
Thanks, Sarah. So one of the primary motivations for doing risk analysis is the history of cost and schedule growth. Cost growth and schedule delays, the legacy disaster that affects problems of all types. If you're working in the aerospace and defense like I have, you know this is a common phenomenon. When I was marketing my book to get it published in 2020, McGraw-Hill's agreed to publish it, but they want me to broaden the scope to consider all projects. So I had to do a little bit of research. And I found that my background in NASA and the Department of Defense in the US was very consistent with projects of all types, everything from the Olympics to software and IT. DoD and NASA missions are pretty similar to software and IT cost growth. 8 out of 10 projects in those arenas experience cost growth. 9 out of 10 experience schedule delays. And for NASA and the Department of Defense in the US, 1 out of 6 more than doubles in cost. In software IT, a quarter of them more than double in cost. And that's a big deal. It means there's a lot of risk. It's very common. It's very frequent. It's high. The average growth is around 50% or more for cost, and not as much for NASA and DoD, but the percentage increase in software is even higher, and it's extreme. So if we go to the next slide. And also, if we look at our risk analysis record, we don't tend to do very well. One of the ways to get better at something is to look at your performance, see how you've done, and then make fixes. But we don't tend to do that in our profession in terms of estimating cost or estimating schedule. And there's very little data for schedule. There's a little bit of data for cost. And if I collected 10 projects, I include my book. 2 of these I worked on. One of these we'll discuss in detail in this presentation. And you would think that, and when you say the term 90% confidence level, when you do a risk analysis, there's a range, basically an infinite range of outcomes. And a 90% confidence level is jargon that means a 90% probability that the actual cost won't exceed the specified amount. So it's a percentile on a cumulative distribution function. If we look at that data, for 8 out of the 10 missions, the actual cost was greater than the 90% confidence level. And that's the opposite of what we expect. We saw 10 missions. You would think, well, probably more like 9 of them would be at or below the 90%. We actually see the opposite. So it's extremely unlikely to see this occur if these risk analyses really are accurate. So it's really the case that it's not. You're more likely to be struck by lightning than for these risk analyses as a whole to be accurate. The mission that we're going to talk about is the top one, which had 0% cost growth, and the risk analysis 90th percentile was greater than the actual cost. And with that, I'll turn it back over to Sara to go over some of the mechanics of this process and how it works.
Thank you. So let's talk about some of the motivations for collecting and dealing with data. We could talk about the motivation for machine learning. Aside from just using it for JCL parametric analysis, we use it because data is the foundation of sound estimates, and we spend most of our time as cost analysts collecting data and normalizing data and verifying that data. And as we all know, it's not always possible to collect a lot of data, and when limited data is available, which happens more often than not, you can use Bayesian methods to leverage as much data as possible. And oftentimes we encounter what we call the curse of dimensionality, which you're all probably very familiar with, where we collect more variables or columns or rows than data points, being able to fill in those columns, for example. In this case, you can either reduce the number of variables you've considered or use machine learning techniques. So what are the benefits of joint confidence level analysis and machine learning, and how do they work together to perform the analysis? For the joint confidence level, it influences decision making and provides a holistic view of the project outcomes given a program's level of risk and uncertainty. Second, it illuminates correlation between cost and schedule. And third, it helps to create and manage credible project plans. Some benefits of machine learning is that it provides better insight into your data. If you have large data sets with many predictor variables, you can use clustering to understand how data can be better grouped or stratified to get to a solution quicker. Machine learning methods can help improve predictive accuracy. Some techniques, such as regression trees, are very useful when you have a lot of categorical data in your data set. Other machine learning methods include ensembles and imputation. Machine learning would separate signal from noise and prevent from overfitting. When you have smaller data sets, you can use imputation to fill in holes, such as when you have more variables than data points. You can also use Bayesian methods, or what we call chained equations, to perform multiple imputation. So now we'll talk about the 2 different JCL methods. The first one is the top-down approach, and then the next one is the bottoms-up approach, which many of you are probably more familiar with the bottoms-up approach. But on the other hand, for the top-down approach, the parametric method would start with a cost and schedule estimate. Uncertainty analysis is applied to each the cost and schedule estimates to generate 2 separate cost and schedule S-curves, or cumulative probability distributions. The 2 S-curves would be combined using joint probability methods to develop a joint probability distribution. Next, the bottoms-up approach, we start with 3 elements. The first is the cost estimate, then the integrated master schedule, and then a risk register. By using the bottoms-up method, you would use a resource-loaded schedule and cost estimate, and then risk analysis would be done at the lowest WBS element level. The bottoms-up method is more time-intensive and can be done in some software, such as ACIT, using JAX and Microsoft Project. The JCL, when all three combined, using those softwares, both the integrated master schedule, the cost estimate, and risk are all three combined. Now we'll discuss the key differences between the bottoms-up and the parametric approach. The bottoms-up method tends to underestimate risk. It ignores unknown unknowns, which would largely be captured in the parametric historical data when using the top-down approach. However, the results between the two methods are similar, as was shown on the example to the left for the now canceled Ares 1 launch vehicle project for NASA. And speaking of NASA, NASA is an agency that does implement a JCL policy. The chart to the left shows the 65% and the 50th percent JCL percentiles using the top-down and the bottoms-up approaches. As you can see, the results are very close. Here's a process map using 6 steps for the top-down parametric approach. In step 1, we start with the cost and schedule data. You would collect cost and schedule data separately. Next, you would use the cost and schedule data to develop cost and schedule estimating relationships using analogies from historical data for each of those, the CER and the SER. In step 3, you would generate your cost and schedule analysis. In step 4, you would perform risk and uncertainty analysis on the CER and SER, including uncertainty on the inputs and estimating uncertainty on the regression equation, while also accounting for technical uncertainty. Next, you would calculate the cost and schedule confidence levels separately. And then in the last step, you would combine the cost and schedule risk analysis into a joint probability distribution to calculate the joint confidence level. Next, I'll hand it over to Kim to discuss different machine learning techniques and how it can be used in the top-down parametric JCL method.
Thank you, Sara. So machine learning techniques are widely used across all of the industries that I'm sure that each one of the participants in this conference actually work in. And so with data being captured at a rate of basically speed at this point where there's an abundance of data available at our fingertips, that it's just great to be able to incorporate these machine learning techniques and using these and doing cost estimating as well. And so it may be a new phenomenon when you think of cost estimating and incorporating some of these machine learning techniques, because you may not have always associated the two, but if you've developed any models, any cost estimating relationships or schedule estimating relationships, you've already actually been using machine learning techniques because you've been building linear or multiple regression models. So machine learning techniques can be useful in the development of CERs and SERs when applying the top-down JCL parametric approach. So we're not going to dig too deep into, all of the methods that exist, but we will talk about some of these that you'll see presented on the slide in front of you. So clustering is an unsupervised machine learning technique that's focused around grouping most like data points together and identifying relationships that may not be so easy to uncover just at initial glance. And so we have regression trees, and those are very useful for data exploration because you can build a basic tree using your raw data without any encoding to convert your categorical variables to numeric variables if you want to just start out with your data set and just try to figure out, which variables are related or most influential to your dependent variable. And so we've used this method in our analysis, and we'll discuss the output in detail shortly. Then we have imputation. And imputation is a handy pre-processing machine learning technique that will allow you to fill in missing data in your data set to preserve as much of the available data that you have. this technique, one of the techniques that we often use is MICE, the multiple imputation by chained equations method. And it estimates your missing values by calculating multiple complete data sets based on the observed values within your data set. And so this is a great method because it helps to reduce bias and improves validity within the data set. Another machine learning technique that is more focused on understanding textual data is natural language processing. And this technique is helpful when you're like searching through really large text documents and trying to answer really tough questions quickly. So it's able to parse through a text document and be able to see if you provide keywords, if those keywords are present in that document, and let you know if that's one that you need to read further or capture data from to help you to answer whatever questions you're answering for your clients. Next slide. Okay, so optimization. Optimization is a core component of machine learning since most algorithms can be formulated as an optimization problem. So you're going to have a goal, and it's either to minimize or maximize some function, which allows comparison to determine the best fit or an optimal solution. The basic elements that will need to be defined are the variables that can be adjusted by the algorithm as it computes, the constraints, which are the boundaries that the parameters must fall within, and the objective function. Next slide. So we have a lot going on this slide, but we performed optimization using a method developed by our own Dr. Christian Smart. And this method is called the maximum likelihood estimation for regression of log normal error, or we affectionately call it Merlin. So Merlin is a technique that estimates the mean log normal without using log transformations on our actual data. So it estimates the power equation and minimizes the negative of the likelihood directly by using Excel Solver, which is a package that's easily accessible within Microsoft Excel. This method is particularly useful since it minimizes the bias in the cost estimating relationship. And bias is how far the average predicted values are from the actual values. Models with high bias are typically underfit, which is a no-no because we are missing some of the true patterns within the data by using an oversimplified model. So just as models that are overfit are bad, we also don't want underfit models because we are just missing out on some of the information that our data is trying to speak to us. Merlin can be executed, again, with Excel Solver, and so by following the steps that are outlined on this slide. So just to run through these, and if you have any questions, please reach out to us and we can provide you the spreadsheet so you'll be able to easily calculate these using your data to be able to incorporate this method on some actual data that you have, but I'll walk you through some of the steps. So we'll always begin using Merlin by calculating a CER with our data that we have. And so that's going to be our starting point. And we do this by using the array linnest function within Excel. And so in your spreadsheet that you'll set up, you define the variables that will be needed for the Merlin calculations. We'll obtain the intercept and coefficients for the independent variables using the linnest output that we get from running our initial model in Excel, and calculate a starting point for theta as the standard error of the Y estimate. And then we take the number of observations in the data set for our N. Next, we calculate the estimate using the CER, and we calculate the percent error, the difference between the estimate and the actuals, divided by the estimate, the log likelihood, and then we calculate the standard error. Next, the negative log likelihood, Pearson's R squared, which is our correlation between the Y and Y hat, and then the standard percent error and bias are also calculated. These formulas will be provided in the spreadsheet if you decide that you would like to do this and try it out on your own. So once all these metrics are calculated, Excel Solver is used to optimize the original CER that we have provided. The objective is going to be set to minimize the negative log likelihood, set the changing variable cells to the intercept, the coefficients for the independent variables, and theta. And then make sure that you uncheck the box that says make unconstrained variables non-negative, and then you hit solve. And the algorithm will converge on a solution, and the values within the spreadsheet will all adjust. So using Merlin, we got a model with a very low bias in our software program example, with peak staff and ESLOC being used as independent variables to estimate our total effort in hours. Next slide. So SERs are a little tricky, especially trickier in comparison to CERs. And when we tried to build a SER, our schedule estimating relationship, using traditional parametric methods, we could not obtain a model with favorable results. The Pearson's R-squared was really low and the error was really high with the model that we developed. And the reason that you often encounter this when you're creating schedule estimating relationships is because schedule does not vary as much in terms of magnitude as we see with costs. And so that makes our results just less significant, typically across the board. To combat this issue, we used a regression tree to fit our data and estimate total hours. For our software data, we were able to fit a regression tree and obtain a Pearson's R-squared of 50%. This may still seem rather low in comparison to some other models that you developed and some of the results and statistics that you get from those, but for SERs, this is a pretty strong showing. So we'll talk a little bit about how the regression tree works by looking at the diagram at the very bottom of the slide. So you think of a regression tree as an upside down tree with all of our data points at the very top, and that's our root node. And the tree splits based on the most influential independent variable to the dependent variable that you have identified. And the first split occurs with the answer of the first question. A yes response sends you to the left, a no response to the right. And once the error has been minimized, the splits end in a terminal node, and you'll see those identified in green at the base of the tree. And the data points that remain with each of the final groupings are averaged to provide an estimate of the dependent variable. So that provides your y hat. Next slide. Okay, so I'll just walk you through the tree that we built using the software data to estimate schedule duration. So all of our data points are at our root node, and you'll see that at the very top in red. And so our first decision node, the first question that is asked is, are total hours less than, a given number? So if yes, then we go to the left. If no, we go to the right. And so if we follow along the left side with our yes, we have another question that basically is trying to determine what's the operating environment for this particular data point. Is it air vehicle, surface vehicle, or, a few other options there? And if yes, you go to the left, and if no, you go to the right. And so the splits end in the terminal nodes that you see all across the bottom. And you'll see that the percentages all tally up to 100%. And so this lets you know how many of the data points are included in each of the nodes. And so the total, of course, will be 100%. So all of our data points will fall into one of the 4 nodes that you see at the base of the tree. And so within each of the terminal nodes, you'll average the points that are there, and this will be your y hat value. So this will be your estimate based on your SER regression tree. And so hopefully that explains clearly, if you haven't seen the construct of a regression tree, this is a good diagram that hopefully helped to explain what you can expect and how you would interpret this if you use this for developing a CER or SER in your analysis. And so now I'll pass it back to Christian to discuss how to best estimate uncertainty in CERs and SERs.
Okay, next slide. So we'll talk about how to do the estimating uncertainty for CERs and SERs. With CERs, you have the parametric uncertainty, and with SERs, you have the parametric uncertainty. So you have regardless of the parametric method used, even if you know the independent variables, the inputs precisely, the regression equation still will not be certain. You will not have a perfect fit. So there's some error term in that. Typically with cost, it's a multiplicative error term. Sometimes with schedules, it may be additive. And so you can get an error term just from that. You also have to add to that and then convolve with that the uncertainty around the inputs. You typically don't know those in advance either. So you have to combine those. You can get standard errors, and you can also get prediction intervals around those. Okay, next slide. And this is just some of the mechanics of how to do it mathematically. You have your uncertainty around your inputs. If you have 3 values, and so often with parameter uncertainty, that requires some amount of judgment. Oftentimes the best way to get and solicit that judgment is to get a low, a most likely, and a high value. That's a triangular distribution. You can calculate the mean and the standard deviation of that with the equation on the right top. The estimating uncertainty, oftentimes I've seen it over and over again that the uncertainty around that is a log normal distribution, and you can determine the mean and standard deviation in log space and then translate that into linear space. And then we assume that those two sources of uncertainty are independent of each other. And basically, in a multiplicative error term equation, you multiply them together. You're not adding them, you're multiplying them. It's the uncertainty around the parameters on the output estimate, as well as the uncertainty around the error term, the residual. So they're independent, and you can use the propagation of errors formula. If you've done any kind of signal processing, you may have come across this, where you look at the mean of x times y is the product of the means. And then the standard deviation formula is a little more complicated. It involves 3 different terms, but you can get that. And so that you do that, and then you basically assume that tends to fit a log normal, which from practice, I know that this has worked well in practice. Okay, next slide. And then, so in the case of the regression tree uncertainty, as Kim mentioned, we did not get good goodness of fit statistics for some of the software schedule development data that we had. However, and really not good is kind of being kind, because basically when we try to regress duration against the things that we thought would drive it, such as the team size and the amount of function points or the amount of lines of code, we found almost that R squared was basically 0. So there was no correlation between the two. So the good thing about software data and the data set that we had is there were numerous categorical variables, all sorts of things. So we used that categorical data along with the continuous variables to develop a regression tree that was much better fit. For this case, we assumed triangular distribution on the inputs, and then we fit the residuals from the regression tree, and it turned out to fit a Gaussian or normal distribution well. Determine the mean and variance from that. And if you look at the residuals there on the left, you can kind of say, yeah, it looks kind of like a normal distribution. There's a little bit of not quite completely symmetric, but it's probably the result of a sample size. And so we assume that those are independent. The errors in this case are additive. When you're using Gaussian normal distributions, those are typically additive errors. And schedules don't tend to vary as much as cost. So, that tends to lend itself more to additive type error. So we did a simulation. We did the uncertainty analysis simulation. We took to 1,000 trials. In each draw, we simulate the inputs. We run the SER. We schedule estimating relationship. We got our schedule prediction. We simulate a residual, and we add the results to the two. So that calculated the total uncertainty for that. Okay, next slide. And then they're talking about parametrics. So after we have these two sources of uncertainty, we have our cost uncertainty and our schedule uncertainty. I said the cost uncertainty tends to fit a log normal. The schedule uncertainty, tended to fit a normal distribution pretty well. we determine what our point estimates are for the project cost and project schedule. We have the probability distributions around these as well. And we can consider these two as the cost is log normal and the schedule is normal. These are marginal distributions of a joint probability distribution for cost and schedule, bivariate distribution. The only thing that we need in addition in terms of that assumption is that so this is a bivariate log normal normal. The marginal distribution for cost is log normal. The marginal cost for the marginal distribution for schedule is normal. The only thing that input that we need to complete this is correlation. The only other factor that's involved in that. So you have a bivariate log normal normal. You need a correlation factor. It's in the linear correlation, the Pearson product model correlation. And that's based on historical data. I've done studies on this in the past. Other people have done studies, and the correlation is pretty high. They tend to drive, they tend to go together pretty well. They don't completely move in lockstep, but they do tend to move together pretty well. And correlation between cost and schedule is typically 60 or 70%. So go back one slide, I think. Yeah, go back, okay, go down one slide. So now we'll talk about, I developed a tool in Excel to calculate this. And you can input the things that are in blue are inputs. So you can input your mean and your sigma, which is the standard deviation. And then you choose, drop down, choose normal or log normal. You input your correlation. And then the other factors that are there, the things that are kind of in lighter font, not colored in blue, are just some intermediate calculations that are done. You can also put in your budget, your project schedule, and then you just hit the macro button, put the little button to calculate joint confidence, and then it will tell you what your cost confidence level is. So what is the likelihood of achieving that budget, which in this case is 71.5%. Schedule, though, is very tight at 40 months. So your schedule confidence, the chance of meeting that schedule, of coming in at or below that schedule, is only 22.9%. And then the joint confidence, the joint risk analysis is more stringent because both of them have to achieve. So only the values that are come in at or below 600 million, in this case, $600, but probably, in terms of large projects, 600 million, and schedules that come in shorter than or equal to 40 months will meet the criteria. So you could achieve the budget value, but not achieve the schedule, and vice versa. So it's a little more stringent. So the joint confidence level is always less. So in this case, the probability of achieving both the budget and the project schedule is only 21.7%. Okay, go to the next slide. I think that is basically it. So this is pretty easy to implement. It's pretty quick to use as well. So I'll turn that back over to Sara, I think, to talk about the results.
Yeah, so we'll talk about what does JCL results look like in a presentation, and how would you explain it to your management? So first, looking at this example of a top-down JCL output, on the y-axis is schedule, and in the x-axis is cost. The cost and schedule ISO curve on the graph represents a JCL confidence level percentile. So you see the different percentiles from 10% all the way up to 70th percentile. In this particular example, the project plan has a $435 million budget and a 43-month schedule. Looking at the graph, the project plan position is at the 24% JCL. If management desired to achieve a 50% JCL, you would need an additional $90 million and 6 months of added schedule. The agency's JCL objective will provide information on how much additional funding and schedule is needed to achieve a more realistic budget and schedule to make the project more successful. Now let's look at another example of a top-down JCL result using the parametric method for the software program example. The benefits of JCL to management would include knowledge of an integrated picture of schedule, cost, and risk early on and throughout the life cycle. For NASA, the JCL policy shows evidence that it enforces better project management and executive decision-making. The JCL will help determine if the results match the project's expectations, and then the agency's JCL objective will provide information on how much additional funding and additional schedule is needed to achieve a more realistic budget and schedule to make the project more successful. So we'll finish off the briefing and presentation with a case study of the NASA MAVEN spacecraft program that used the top-down parametric JCL method. In 2009, the MAVEN spacecraft program had an estimated JCL of 23% with the project cost and schedule plan. If a year was added to the development schedule, the JCL was estimated at 44%. Looking at the JCL ISO curves, in order to achieve a 50% JCL, you would need to add an additional $50 million in 8 months of schedule. To achieve a 70% JCL, you would need an additional 77 to 195 million and an additional 11 to 21 months of schedule. In 2013, the actual cost and schedule for the MAVEN program came in at the 50% JCL estimated in 2009. So this is an example where the top-down parametric JCL method was used and it actually was estimated quite accurately from the 2009 estimate when the program actuals came in 2013. That is the conclusion of our presentation. And now I think if we have any time for questions, I'm not sure, we're 1 minute over our timeline, so I'll hand it back over to Pierre.